Hi everyone, it's my pleasure to present this work. The title of the presentation is MEMS sensor data anomaly detection for the UAV flight control subsystem, and I'm from Harbin Institute of Technology. This is outline. It includes 5 parts. First, let's see the definition of UAV. It is also called the unmanned aerial vehicle. From this picture, you can see the relationship among target plate, aircraft, missile, and UAV. The features UAV include 4 main features, which is it is controlled by our onboard computers or by a remote pilot. It is also launched and recovered by automatic system or external operator. Some degree of the automatic intelligence can take corrective action when a fault occurs. And it also can return payload data and housekeeping data. You may be familiar with drone. In the military, it is a target used in missile testing. In the military area, the technology of UAV is the most advanced. It has been through 3 phases. The first is target drones, which provide ground and aerial gunnery target that simulates enemy aircraft or missile. The second is the reconnaissance, which provides the battlefield intelligence. The second is the combat, which can provide attack capability for high-risk missions. Here I introduce 2 famous UAVs, which are both produced by the US. The first one is MQ-1 Predator. Its primary function is for armed reconnaissance, and the second one is the RQ-4 Global Hawk. Its primary function is for surveillance and reconnaissance. The other parameters you can be found in this slide. The architecture of the UAV is mainly constituted of 6 subsystems, which are guidance subsystem, propulsion subsystem, remote control and telemetry subsystem, flight control subsystem, airframe subsystem, and launch landing subsystem. In this study, we aim to enhance the reliability of the UAV flight control subsystem. As we all know, the sensor may become fault when it is installed in a UAV, but the wrong output data of the sensor may bring the wrong decision to cause some catastrophe. The challenge in this area is that the sensor has different fault counts. Some are stuck, bias, drift, scaling, and noise. On the right figure, you can see the black curve is the normal output of the sensor, but when it is stuck, the output became the red line, and the green one denotes that the sensor has become the bias fault, and the blue one denotes that the sensor is the drift fault. How can we found the sensor fault is important for the UAV operation. In general, the sensor data has three kinds of anomaly, which are point anomaly, contextual anomaly, and collective anomaly. In this picture, you can see that the O1, O2, O3, the data in these 3 zones are different from the most data in N1 and N2 zones. So we can call them a point anomaly. In the second contextual anomaly, we can see that in the circle zone, the data isn't has the same trend with the data before and after them. So we can call them contextual anomaly. And in the third picture, in the circle zone, the data also has the feature of a period output. But in this area, the data became almost the same. We call this is a collective anomaly. So we propose one method based on the kernel principal component analysis, which is KPCA, to detect the anomalous sensor data. It includes five steps in this method. After we got the raw sensing data, and we should divide them to the training and testing data. Then by using the training data, we can train KPCA model. After we got the trained KPCA model, we can carry out the following anomaly detection. Finally, the detection results will be analyzed. Uh, it's important to note that the UAV has different flight modes, such as the takeoff, climb, cruise, land. In these different modes, the raw data have different features. So when we analyze this data, we should segment this raw data with the flight mode. Then we can carry out all the two main steps for the sensing data anomaly detection. Uh, the specific steps in this figure gives the main parameters we need to get. To weight the performance of the anomaly detection, we can use three metrics. The first is the false positive ratio, which indicates the percentage of the normal data detected as the anomalous data. And the second is the false negative ratio, which means that the percentage of the anomalous data detected as normal data. And then the last one is accuracy, which means that the normal data detected as anomaly and the anomalous data are detected as anomalous. Here is our experimental evaluation. It includes the four rotors unmanned aerial vehicle and its remoter, a computer with mission planner. In this picture, this is a data acquisition. You can see that this little PCB is the MEMS sensor with it, and this MEMS sensor includes 3-axis gyroscope, 3-axis accelerometer, and 3-axis magnetometer, and one altimeter. In this mission planner, we can carry out some parameter configuration before flight. This is give the main parameters which needed to be calibrated. It's accelerometer, compass, remoter, and also the flight mode selection. And in this after flight controlled by this mission planner, the data are exported, and we can analyze the data we got. Here is a video we carry out the experimental. Let's show you. You can see it climb from ground and fly in the sky for a few minutes. The box under the UAV has the data acquisition system, so the data we can get after it landed. Yeah, let's stop here. So These four figures illustrate the data we collected after the UAV landed. And we can see the three-axis accelerometer and three-axis gyroscope and three-axis magnetometer and the raw data of the altimeter. And in the following analysis, we use the accelerometer, gyroscope, and magnetometer data used as the training data. And the altimeter data are used as the target data which we carry out the anomaly detection. In the right figure, you can see that the SP value, which is in the KPCA, we use KPCA to get. If this value is larger than threshold, we got from the training data, it is labeled as the anomalous data. And this table gives the three experimental results. We can see the FPR values are smaller than 5%, and in the domain of the anomaly detection, it is a better result. Conclusion, in this study, one kind of data anomaly detection approach for UAV sensing data is proposed, and the approach has good performance at detecting the anomalous data by the practical flight sensing data of UAV. In the future, the different mode of UAV flight will be carried out with MEMS sensing data. Thanks. That's all.
Thank you very much.